So welcome back. Let's continue lecture number 3 and new chapter. This chapter is about the moisture properties and conditioning processes. Chapter 3 is from McQuestion. Right. So let's have first the introduction about the moisture and the standard atmosphere. When we say the atmosphere, we know that the atmospheric air is a mixture of many gases plus water vapors and numerous pollutants. Right. So basically, when we say our atmospheric air, that mainly composed of three constituent. One of them is the water vapors, right? Water vapors, some gases, let's say many gases, water vapors, or maybe some pollutants that include maybe the dust particles. So mainly we have the three main component, right? But out of these three component, the composition of the dry air, I mean the first one we call the composition of the dry air remains constant, almost constant. It may vary slightly with time, location, and altitude, but it's almost remains constant. And the composition of the dry air is fixed by the International Joint Committee on Psychometric Data, and that fixed composition is provided in table 3-1, which says that the dry air mean the constituent the composition consists of oxygen, nitrogen, argon, and carbon dioxide. And you can see the on the basis of volume fraction, about 20.95% is oxygen. I mean, approximately, let's say 21% is oxygen, then 78% is nitrogen, and remaining approximately 1% is a combination of the argon gas and carbon dioxide. So this composition of the dry air is not fixed, although actually it can vary depending upon the time, location, and altitude. But that International Joint Committee, they have fixed the composition of the dry air, right? And when we say the standard atmosphere, I mean, when we use the word that standard atmosphere, the standard atmosphere, let's say the US standard atmosphere mean, first of all, the acceleration due to gravity will have a value of 9.807 meter per second square. And the standard temperature mean it's about 15 degrees C or 288.1 Kelvin, and the pressure will be equal to 101.039 kilopascal, right? And the atmosphere that consists of the dry air will behave as a perfect gas. So this is the meaning of the standard atmosphere, in which you have to define the value of the G, the standard temperature, the standard pressure, and that dry air will be acting as a perfect gas. So that's actually the meaning of the standard atmosphere. Now, once you have defined the standard atmosphere, in that atmosphere, the value of the universal gas constant, as you know, it's 8,314 joule per kg per mole Kelvin, or in terms of the British unit, that's equal to this one. But in case of the numerical problem, we'll just follow the SI units only. There is a mixture of the problem. Some of them they are based on the British units, some are based on the SI unit. So mainly we'll focus on the SI units, right? And if we know the universal gas constant, then we can calculate the gas constant. As you know, gas constant can be calculated by dividing the universal gas constant with the molar mass, right? Molar mass, this is for, let's say, vapors. V mean for vapors, I mean water vapors. You know, the molecular mass of the water vapor is about 18.015. So we can get the value for both in British unit and in SI unit, the value of the gas constant for water vapors. Similarly, we can calculate the molar mass for the dry air. You have to divide the universal gas constant with the molar mass. You can add up all these values, then you divide with that, you will get the value gas constant for the dry air. And then the ASHRAE handbook, which is provided in reference 3 of that book that summarizes the standard atmospheric data for different altitude. You know that the atmospheric pressure changes with the altitude, and they have estimated by using that formula that the atmospheric pressure may vary according to the altitude. So that depends on these two constant A and B. So they have provided a range of the value for A and B for different altitude. For example, in table 3.2, it is mentioned the value of the constant A and B for two different heights when the altitude is equal or less than 4,000 feet, or when the altitude is greater than 4,000 feet, then you can use the value of A and B both for the and that's the I think the inch pound unit, and this is for the international units, right? In kilopascal, right? You can see there is a slightly variation, let's say in atmospheric pressure, right? So when the altitude is less than or equal to 4,000 feet, you can see, I mean, we are using 101.325 kilopascal. But if the high, I mean, altitude from the sea level is higher than the 4,000 feet, then the value of the atmospheric pressure is different. So that is provided by that empirical relation is provided by the ASHRAE handbook. That's available in the ASHRAE handbook. But mainly, I mean, our most of our numerical problem or problem that will be based on the SI unit, and the altitude will be considered equal or less than the 4,000 feet. I mean, we are going to use this SI unit for the atmospheric pressure. Now, there are several fundamental parameters that are related to the moist air, and the important of which is first of all the enthalpy of the dry air. Right, enthalpy of the dry air, as you know from the thermodynamics, that's equal to the product of the Cp and the temperature. So if you know the temperature of the dry air, you multiply with the Cp value, that will give you the enthalpy of the dry air. And the Cp of dry air is basically, we can take that value equal to constant 1.005 multiplied by the temperature. Right? Why we can take the value to be constant? Similarly, the change in enthalpy will be Cp delta T. So whatever is the change in temperature, that will give you the change in enthalpy. Delta T will be multiplied with the constant value of Cp, then you can get the change in enthalpy of the dry air. I mean, we can know basically this is the range of the air conditioning temperature. Most of the air conditioning processes, they are in between the minus 10 degrees C to 15 degrees C. And you can see the variation in the Cp is very negligible. I mean, the variation is even less than 0.2%. I mean, even less than 1%. So that's why for the air conditioning application, we assume the value of the Cp to be constant. So we can use this formula for calculating the value of the enthalpy of the dry air. Now, likewise, I mean, we can also calculate, since the moist air is a mixture of the dry air and water vapors. So if we individually calculate the enthalpy of the dry air, that will be equal to Cpt. Similarly, the enthalpy of the water vapors, we can calculate by using the ideal gas equation, right? We know that for the vapor pressure of the water vapors in atmospheric air is very small. We know from the knowledge of thermodynamics 1 and 2, when the partial pressure of the water vapors in the atmosphere is very low, then we can assume water vapors to be an ideal gas. When we say ideal gas, the meaning is that the enthalpy is a function of temperature only. We can also see that from the graph of temperature and enthalpy. As you can see, in case of air conditioning application, the temperature is below 50 degrees C. I mean, this is the range for the temperature. And for that range, in this region, I mean, the value of the vapor pressure is in this range. And you can see if the temperature is constant, enthalpy is constant. For this particular temperature, if the temperature is constant, enthalpy is constant. So that's why the enthalpy of the water vapors can be equal to the enthalpy of the saturated vapor at the same temperature. So whatever is the enthalpy of the saturated vapor, same enthalpy is here, same enthalpy is here, right? So the enthalpy is constant. So for a simplification, for the for easy calculation, we can assume that the enthalpy of the water vapors can be taken as the enthalpy of the saturated vapors. Right. So there are two options for calculating the enthalpy of the water vapors. If we know the temperature, we can read that enthalpy from the steam table, right? The other option is there is an empirical relation. You put the value of the temperature here and you can get the value of the enthalpy of the water vapors, right? Both in this is for the SI unit and the next relationship is for the British unit, but mainly we'll focus on the SI units only. So here you can calculate the enthalpy of the water vapors. I mean, for this particular range, this empirical relation is applicable, not for all the temperature range, right? So you can see that we are using, instead of HV, we are using that symbol Hg. G is representation of the saturated vapor. I mean, the enthalpy of the water vapors is basically equal to the enthalpy of the saturated vapor, Hg, right? So the value of the Hg can be we can read from the steam table or by using this empirical relation. It's up to you. The variation is very small, negligible one. So, right? So either of the relation can be utilized to calculate the enthalpy of the water vapors. Right, so let's continue. Another fundamental parameter that are related to the moisture properties. Another one is the pressure. Now, the moisture is a combination of the water vapors and a dry air. So when we say atmospheric pressure, so atmospheric pressure is a combination of the partial pressure of the dry air and partial pressure of the water vapor. So the total atmospheric pressure is a combination of the partial pressure of the dry air and partial pressure of the water vapors. Since we have assumed that water vapors and dry air can be assumed as an ideal gas. So each one can be calculated individually by using an ideal gas equation. Let's say if you want to calculate the partial pressure of the dry air, then the above equation will be used as PA, VA, right? RA, TA, right? Similarly, I mean the Dalton's law, if you remember that for calculating the ideal gas mixture, we use the Dalton's law, right? Similarly, if you want to calculate the partial pressure of the water vapors, then instead of A, we'll use PV, PV mean for vapor, similarly VV, right? T will remain same because for the Dalton's law, the temperature should be same for the mixture, right? Right. And the next fundamental parameter we called absolute or specific humidity. It also called humidity ratio. It has three different names: absolute humidity, specific humidity, or humidity ratio. But most of the time, I mean, most of the book, they use the specific humidity, right? And specific humidity, as you know, this is basically the mass of water vapors present in unit mass of the dry air. This is basically the ratio. Let's say for a certain area, let's say in our room, right, whatever is the mass of the water vapors present in the mass of the dry air, that will give you the specific humidity. As you know, this is MV, that's the mass of the water vapors present in the mass of the dry air. Right? And we can also, I mean, the unit for the omega or this humidity ratio is kg of water vapors per kg of the dry air. We can also convert this relationship, I mean, in terms of pressure, as you know, that we can convert like MV. If we apply the ideal gas equation, MV will be equal to PVV divided by RVT. Similarly, the MA will be converted as PAV divided by RAT, since volume in a specific room is same for water vapors and the dry air. So if you cancel out, the remaining will be PV divided by R. So this is a gas constant for water vapors. As in the first slide, I showed you the value of the RV, as well as we can also calculate the gas constant for the dry air. So if we put this constant, then we get another constant. And the value of that constant is 0.622. And then we'll have PV divided by PA. So this is our relation for the specific humidity, right? I mean, this PA further, I mean, this PA will be equal to this one will be equal to P minus PV. So we can transfer this PA P minus PA, right? From here, we can calculate specific humidity. That means you should know the atmospheric pressure. The atmospheric pressure is already known to us, which is equal to 101.325 kilopascal. But we need to know the value of the partial pressure of water vapor. And these partial pressure of water vapors, as you know, as I explained earlier, we can calculate from this ideal gas equation. And then we can calculate the value of the specific humidity. Then we have another type of the humidity, which is called relative humidity. It is represented with the value phi, right? This relative humidity is represented with phi, whereas this specific humidity is represented with the term omega. Now this is basically the ratio of, this is basically relative to saturated condition. I mean, this is the ratio of the amount of the water vapors, I mean, amount of the moisture the air holds to the maximum amount of moisture the air can hold at the same temperature. Maximum amount means the saturated state, right? So basically, let's say if let's say in that room, let's say this is our room. In that room, what is the value of the moisture currently? Let's say the value of the moisture mean MV. What is the mass of the moisture currently? And if same room is filled with the saturated state, I mean maximum amount of water vapor. So this relationship is represented in the form of relative humidity, right? So relative humidity is basically the mass of the water vapors currently present to the mass at saturated state. Again, we can convert this mass in terms of pressure. So we can also represent the relative humidity as the ratio of the current vapor pressure to the saturated vapor pressure at the same temperature, right? And then based on, let's say this is equation 1, this is omega is equation 1, right? And then we have phi, let's say this is equation 2, right? So we can relate equation 1 and equation 2 because in the same equation, we have PV and here also we have PV. So let's say from this PV, if we put this PV in equation 1 and if we rearrange and simplify, then we can have the value of the phi in terms of omega. Similarly, we can have omega in terms of phi. Right? So we can relate phi and omega. Then another fundamental parameter in the moist air property is enthalpy of the moist air. Up till now, we have discussed the enthalpy separately. Enthalpy of the water vapors, right? That is basically the enthalpy of the saturated water vapors. That can be calculated from the steam table or that can be read from that empirical relation. Similarly, we discussed the enthalpy of the dry air, right? And dry air means CPT. The enthalpy of the dry air can be calculated from CPT. What about the combined, I mean, enthalpy of the moist air? How to calculate the enthalpy of the moist air, right? Right? I mean, basically the mass of the dry air is not changing. In practical, I mean, the mass of the dry air is not changing, but the mass of the water vapors is changing, right? So that's why we need to express enthalpy in terms of mass per unit mass of the dry air, right? When we say the enthalpy of the moisture, that should be represented as the enthalpy of the moisture is basically enthalpy of the moisture per kg of the dry air. I mean, let's say the total enthalpy, of the atmospheric air, which is also called the moist air, is the sum of the enthalpy of the dry air and water vapors. I mean, mathematically, I mean, the enthalpy of the moist air is the sum of the enthalpy of the dry air plus enthalpy of the water vapor. This is in the, I mean, the explicit form. If we convert in the implicit form, then the total enthalpy is mass into enthalpy. Similarly, capital H is mass into enthalpy. Now, if we divide this with mass of the dry air, then this is small h. That small h is basically the enthalpy of the moist air, but per kg of the dry air. So that's the representation that we should represent the enthalpy of the moist air as the enthalpy of the moist air per unit mass of the dry air. So if we divide the above equation, this will be cancelled out. Then we'll have HA plus mv divided by MA then into HA, whereas we know this ratio MAV divided by MA is omega. So this is how we can calculate the enthalpy of the moisture. So enthalpy of the moisture is basically, it has two terms. The first term we called HA, enthalpy of the dry air, and omega Hg is the enthalpy of the water vapors. Right? Since we have replaced that HV as Hg, this is approximately equal, as I showed you in the TH diagram as well. Right? And then the some of the temperature that are used in the air conditioning process, one of them we call the dry bulb temperature. Shortly, this is represented as dBT, right? I mean, we'll not write down the complete temperature all the time. We'll just use the term dBT. That means the dry bulb temperature. And you're familiar with the dry bulb temperature. This is basically the ordinary temperature of the atmospheric air, which is, I mean, measured with the help of common thermometer. It could be the manual thermometer or it could be a digital thermometer. So that's called the dry bulb temperature. And then we have another temperature. It is called the dew point temperature. Dew point temperature, you are also familiar with the dew point temperature. This is basically the temperature at which the condensation begins when the air is cooled at constant pressure, right? This is basically the saturation temperature of the water vapor corresponding to vapor pressure. As you know, this is if you recall that this is basically the TG, saturated temperature of the water vapors at corresponding PV, at corresponding vapor pressure. I mean, on TS diagram, let's say let's take the example of today. Now let's say today during the daytime, let's say the temperature, instantaneous temperature was, let's say, the 10 degrees C, right? And our atmosphere here at GIK, that contains certain amount of the water vapors. That means it will have certain vapor pressure. But as the sun sets, I mean, the temperature falls, but the amount of water vapors in the air remains same. I mean, the pressure is same, but the temperature is decreasing. As the temperature is decreasing, because T1 is larger, so as the temperature is decreasing, then a point comes when the vapors present, they try to condense. So that's called basically the dew point temperature. This is represented with the dPT. So dew point temperature, as you can see here, dPT is basically the saturated temperature at this pressure. I mean, this is the TG. At this point, it's called TG. At which pressure? At PV, because this is a constant pressure. The same amount of water vapor that was present during the day, the same that will be during the night, but as a result of the decrease in temperature, when it is reaches a point to it start condensation. So this temperature is called the dew point temperature. Dew point temperature is also observed in case of the cold drink. I mean, when the outside air, which is called the atmospheric air, or the moist air, when it come in contact with the surface of that tin, then if the surface temperature of that can is lower than the dew point temperature of the air, then the vapors present in the moisture will be condensed, and you can see here the water droplets, right? Same happen nowadays inside of our window. I mean, if you carefully look the window of our room, then the inside, if you observe carefully, then you will see during the morning time, you can see a lot of condensate. That's because during the daytime, I mean, those vapor were present in our room, but during the night time, as the temperature falls, those vapors are condensed inside, I mean, and that are trapped with the glass of the window. Then we have another fundamental parameter. It is called the adiabatic saturation and wet bulb temperature. Now, before I explain adiabatic saturation and wet bulb temperature, the question is why we need that temperature, what is the importance of that? Basically, the humidity, I mean the omega and phi that we discussed in the previous slide, this is basically, as you see in the relationship, they are represented in the form of some indirectly measurable property. Indirectly measurable property mean in terms of maybe PV, right? They are represented, and vapor pressure is not a directly measurable property. That's the indirectly measurable property. So basically, we want to convert that omega and phi in terms of the directly measurable property. Like directly measurable property, what is the directly measurable property? Temperature, right? Temperature and atmospheric pressure, which is also called P. I mean, P is already known to us. We know what is atmospheric pressure. So basically, we want to convert omega and phi in terms of temperature only, right? So that's the objective of this adiabatic saturation and wet bulb temperature. To understand that, let's say this is an arrangement in which the moisture enters at point 1, and when it enters at point 1, then let's say this is unsaturated at point 1 and it has a temperature of T1, omega 1 and phi 1. So as it passes through the box, this box is fully insulated. Fully insulation means no heat can enter or no heat can leave from that box. When the air enters in that, since the as it is because of the temperature of this air, then the water vapors will be vaporized. I mean, that's called the phase change. I mean, the air, because of the temperature of the air, some of the water vapor will take heat and that will be vaporized, right? So assume that this box is very large. This this box is very large, right? So when the air reaches at point 2, it is completely saturated. Completely saturated means the value of the phi is 100%, right? The value of the phi is 100%, and let's say we have temperature T2 and omega 2 at point 2. And the amount of water vapors that vaporize is can be make up through this water at the same temperature equal to T2, right? Now, for this case, if we try to apply the mass and energy balance, then we can calculate the value of the omega 2 as well as omega 1. But the objective is to represent that in terms of temperatures only. I mean, one is the temperature of the unsaturated air and another one is the temperature of the saturated air. So let's try to apply. I mean, this is the graphical representation on the TS diagram of this process. I mean, this is the one, and as a result of the cooling of the air, I mean, because of vaporization, the T2 will be slightly low, right? So let's try to apply the mass balance first, right? For the dry air, you know that whatever is the mass of the dry air at point 1, that's equal to a point 2. So MA1 is equal to MA2. So let's say that's equal to MA. I mean, the mass of the dry air is not changing. What about the mass of the water vapors? Let's say here we have the mass of the water vapors MW1, right? And some of the water vapor as a result of the vaporization. So let's say that's M dot F, and that's equal to the outlet. I mean, this is inlet, again, this is inlet, and this is outlet. So that should be equal to M dot W2, right? So that's called the water vapor. And you know that we can convert this mass of the water vapors in terms of MA omega 1, because the definition of the omega is equal to mass of the water vapors, I mean MW divided by MA. So we can have this mass of the water vapors at omega times MA. So we can convert this mass of the water vapors as MA omega 1 plus M dot F is equal to MA omega 2. So from here MF will be equal to MA will be constant, so it will be omega 2 minus omega 1. So mass of the water vapors is basically the difference of the specific humidity. I mean, omega 2 minus omega 1 multiplied by the MA. Similarly, for this arrangement, we can apply the energy balance. Whatever is the energy entering, that should be equal to energy leaving. So energy entering means the enthalpy of the moist air at point 1. So enthalpy of the moist air at point 1 plus enthalpy of the water vapors. So that should be equal to the enthalpy of the moist air leaving at point 2. And we can again simplify, we can put the value of the M dot F. M dot F is MA into omega 2 minus omega 1. So if we put that value and if we simplify mean we have we can cancel out M because MA is constant, and then we'll have H1 plus omega 2 minus omega 1 times HF2 is equal to H2. Right? Again, if we put this is the enthalpy of the moisture, right? And the enthalpy of the moisture mean CpT1, enthalpy of the dry air plus the enthalpy of the water vapor, which is omega 1 Hg1. Similarly, we have omega 2 minus omega 1 into HF2. And similarly, the enthalpy of the moisture at point 2, that will be CpT2 plus omega 2 Hg2. So from here, we can get the value of the omega 1. So if you simplify, the omega 1 will be equal to this formula. So this is a function of the temperature only. How it is a function of temperature only? I mean, what is T2? T2 is the T2 is the temperature of the saturated air, right? T1 is the temperature of the unsaturated air, right? And what is omega 2? Omega 2 we can calculate from the previous formula. As you know, omega 2 is basically 0.22 is the state of saturated air. So here instead of PV now we'll put Pg2. Similarly, instead of PV, we'll put the value of Pg2. As you know, to get the saturated pressure, you just need the value of temperature. I mean, from the steam table, if you know the temperature, you can read the value of the Pg. Right? If you know the temperature, you can read the value of the Pg. So again, if you look at this relationship omega 1, what you need is you just need two temperatures. For example, you need T2, you need T1, right? For omega 2, you only need is T2, right? If you know T2, you can calculate omega 2. Similarly, what is HFG2? HFG2 is again you need T2, right? Right? What is Hg? Again you need T1, right? What is HF2? Again you need T2. Right? So basically, if you know just two temperature, now the omega 1 is basically the function of two temperature only, which is called T1 and T2. So that means if you just know the two temperature, the temperature of the unsaturated air and the temperature of the saturated air, then you can calculate the value of the omega 1. Once you know the omega 1, since we have the relationship between omega and phi, and then we can calculate the value of the phi. So in this way, by just calculating the two temperature, the unsaturated temperature and saturated temperature, we can calculate the value of the omega and phi. But the question is, how can we measure practically, experimentally these two temperatures? These can be measured with the help of simple arrangement, as you can see in that figure.
Excuse me, sir.
Yeah.
Sir, I had a question. Sir, in the energy balance, why do we only consider dry air and not water vapor as well?
I mean, we have considered this is the mass balance for the dry air, right? And this one is the mass balance for the water vapors, right? And this is the energy balance for moisture. When we say moisture, moisture mean both the dry, I mean this enthalpy is the enthalpy of the moisture. That's why we have written the both component for the dry air and water vapors, right?
Okay. Okay.
So how can we, I mean, these two temperature, how can we measure these two temperature experimentally? T1 is basically simply the dry bulb temperature. I mean, the temperature measured with the help of an ordinary thermometer. That will give you the T1. What about T2? T2 means the temperature of the saturated air. So T2 can be measured when, let's say, a wick cloth is attached with a thermometer, and that wick cloth means that's dip in the water. So when the air will strike on that, that temperature will be equal to the temperature of the saturated air, right? And nowadays we have the temperature. This is called sling thermometer. This sling thermometer basically is giving you the two temperature at the same time. For example, the one bulb is giving you the dry bulb temperature, which is experimentally says T1. This bulb will give you the temperature of the unsaturated air, T1, whereas this bulb, which is attached with a wet cloth, right, that will give you T2 experimentally. We assume that the bulb inside is saturated now. So the temperature given by that bulb will be the temperature of the saturated air. So nowadays, what we need is basically we need T1 and T2. So then we can have omega 1, and once we have omega 1, and then we can get the value of the phi. So basically the digital thermometer, what they do, basically they have a small chip inside, and that small chip inside is basically the program based on this equation, these two equation. Basically the sensor is just measuring the T1 and T2. I mean, T1 mean it's measuring the dry bulb temperature, and T2 is the wet bulb temperature. Then programming inside that, I mean, that convert this T1 and T2 to omega 1 and phi 1, right? So this way you, by just measuring the two temperature, the temperature of the unsaturated air and the temperature of the saturated air, you can measure the value of the specific humidity and the relative humidity. And then all these fundamental parameters that we just discussed in the previous slide, we can also calculate those parameters with the help of one chart. That chart is called a psychometric chart. Psychometric charts, they are basically used to calculate the air conditioning processes and the properties of the moist air. I think you are also familiar with the psychometric chart. As you can see, this chart is available in the appendix of the book. That's called the appendix C of that book. And not only one psychometric chart at various sea levels, because each of the psychometric chart is developed for one particular atmospheric pressure. As the sea level, I mean the elevation from the sea level is changing, then the value of the psychometric chart and the data is slightly varying. So that's why one particular psychometric chart is applicable for one set of the atmospheric pressure, right? There is a this protector, I mean D shape. This give you the value of the sensible heat factor. SHF, sensible heat factor. We'll discuss this in a later stage. I mean, in today's lecture, we'll discuss that. And the remaining parameter, I hope you are familiar with that. Basically, the psychometric chart. If you know any of the two properties, we can locate any of, I mean, the remaining properties we can read from the psychometric chart. But what you need to know two properties. I mean, if you look at all of the properties, there are 7 properties that are mentioned on the psychometric chart. One of them we call the dry bulb temperature. So dry bulb temperature is the horizontal line. As you can see, this is the vertical line, right, starting from 0 to 50 degrees C. So this is basically the range of the air conditioning process. So this chart is for 0 to 50 degrees C. So these vertical lines, they are called a dry bulb temperature. Then we have the wet bulb temperature. So these lines, as you can see, 5 degree, 10 degree, 15 degree. So these lines, I mean, these dotted lines, these are the wet bulb temperature lines. These dotted lines, they are wet bulb temperature line. Then we have the dew point temperature. The dew point temperature is basically when the horizontal line, these horizontal line, when it cuts at the 100% phi, these are the phi value. You know that these are the phi values. This is phi value, this is another phi value. So at 100% saturation, when this horizontal line cuts here, this is called the dew point temperature, DPT. Right, at a dew point temperature, or the at the 100% saturation, all of the three temperature, wet bulb temperature, right, dry bulb temperature, and the dew point temperature, which is called DPT, dew point temperature. The three temperature, they are equal at 100% saturation. For example, at this point, 15 degrees C is the wet bulb temperature. So if you drop vertical lines here, so same 15 degrees C will be the dry bulb temperature. So horizontal line, the dew point temperature, again the dew point temperature will be 15 degrees C. Then we have the specific humidity. So this vertical line give you the omega value, right? And then relative humidity is these lines, as I mentioned earlier. Then the enthalpy of the moisture. So these are the enthalpy lines. As you can see, these are the enthalpy line. So this is basically the enthalpy of the moisture per kg of the dry air. The unit is very important. Please take this focus that the unit on the psychometric chart is very important. When we say enthalpy, that's the enthalpy of the moist air. right? The enthalpy of the moisture per kg of the dry air. So similarly, when we say omega, so omega is basically the kg of water vapors, per kg of dry air, right? Similarly, we have the specific volume of the moist air. So this is basically these lines, they are the specific volume of the moist air, these lines, specific volume of the moist air per kg of the dry air. Again, the unit is very important. This is the specific volume of the moist air per kg of the dry air. You can also separately see these lines, I mean these vertical lines, as I mentioned, the 7 properties, one of them is dry bulb temperature. This is vertical line. Then we have the wet bulb temperature line. As you can see, these are the wet bulb temperature line. Then we have the humidity ratio. This is the humidity ratio, which is the kg of the moisture per kg of the dry air. And then we have the specific enthalpy. So this is the chart for the specific enthalpy, which is the enthalpy of the moisture in kilojoule per kg of the dry air. And then we have the specific volume. This is the specific volume of the moisture per kg of the dry air. And then we have the dew point temperature, the horizontal line that cuts on the 100% saturation, 100% phi value. That's called the dew point temperature. And lastly, the 7th property is the relative humidity. I mean, this is the 100% relative humidity, then it slightly decreases as we move in this direction, right? And lastly, we have a different air conditioning processes, right? You are also familiar with these air conditioning processes, and the simplest one is the simple heating, which is also called increasing the temperature. And then we have the simple cooling, I mean, lowering the temperature, then the humidification, adding moisture content, dehumidification mean the removing the moisture contents, and it could be the combination of the above processes. Combination mean it could be cooling and humidification. It could be cooling and dehumidification, and it could be heating and humidification. So on psychometric chart, as you can see, that could be the combination of various processes. For example, the straight horizontal line, that will be the representation of the heating and cooling. For example, if you're moving in this way, heating means you are increasing the dry bulb temperature. The cooling means you are decreasing the dry bulb temperature. When we say humidifying, humidifying means you are increasing the omega value. You're increasing the kg of the water vapor. When you're moving down, that means you are dehumidifying. You are decreasing the kg of the water vapors, right? So that could be the combination. For example, if you're moving in this direction, so that means you are increasing the dry bulb temperature and the mass of the water vapor. So this is the heating and humidification. So if you are moving in this direction, that means you are decreasing the dry bulb temperature. That means you are cooling, as well as you are decreasing the water vapors, which is called the dehumidification. So let's discuss one by one each of the air conditioning process. Let's say the first one is the simplest one. We called it as a simple heating and cooling. So simple heating, let's say this is a typical example of the simple heating process. Let's say this is the outdoor condition. Let's say OD, outdoor condition, right? And we have the indoor condition, right? Let's say the outdoor condition, atmospheric moist air is much cooler nowadays, right? And when that air is can be heated up with the help of, let's say, that coil, right? And that coil could be the electric heating base. It could be the steam heating. I mean, the steam can move inside the coil, so the air can come contact with the surface of that coil, so it can gain heat. So as a result, the heat going into the room or the conditioned space will have the higher temperature, right? So that means if we are not adding or removing the water contents, we called it as a simple heating process. And we can draw on the psychometric chart. Let's say if we know any of the two property, let's say if we know phi value and the dry bulb temperature, then we can locate that point on psychometric chart, and the horizontal line will represent as that this is just a heating process, right? This is just a heating process from 1 to 2, right? I mean, you are just increasing the dry bulb temperature. The T is basically the surface temperature of the coil, right? I mean, this air cannot reach surface temperature of the coil. The temperature of the outgoing air will always be less than the surface temperature of the coil. It could be heating coil, right? So what is happening during the simple cooling? During the simple cooling, only the dry bulb temperature is increasing from TD1 to TD2, whereas there is no change in the mass of the water vapors. In other words, the specific humidity remains constant. What about the relative humidity? What about the relative humidity? What is happening with the relative humidity, the phi value?
चेंज होती है सर.
So, I mean, change mean it is increasing or decreasing?
Decreasing sir.
Yeah, it's decreasing.
Heating is.
Yeah, so that means if you are just heating, I mean, just simple heating, although you are increasing the temperature with the help of simple heating, but you are decreasing the relative humidity, right? In other words, the dryness fraction you are increasing, right? That's why during the winter, it is not recommended just a simple heating. Simple heating is not recommended. Like let's say you burn your gas heater inside your room, right? That's called the simple heating. So inside your room, if you are increasing, then with the increase in temperature, as you are increasing the temperature, the relative humidity inside the room is decreasing, right? Or also, I mean, the air inside that room is used by the burning process. So not only the oxygen content inside the room is decreasing, but also the relative humidity is decreasing. So that's why it is recommended that you should also have some humidifier inside that room, or you should put some water inside the room so that as a result of the evaporation, the relative humidity should not decrease. Right? So during the heating process only, omega remains constant, but the phi value is decreasing. Right? What about the simple cooling? Similarly, the simple cooling process can be achieved with the help of refrigerant. I mean, the outside air, when it come in contact with the cooling coil, right? With the cooling coil, inside could be the chilled water. I mean, we can use a chilled water as in case of vapor absorption process, or in case of a vapor compression process, we can use a refrigerant. Right? So when the air come in contact with that cooling coil, then the air supplied to the room, I mean, this is during the summer season, then that the air will be much cooler compared to the outdoor condition. Now, if you draw on the psychometric chart, that will be same as the above process, but the direction will be opposite. I mean, that will be from 1 to 2. And similarly, the 3 is the surface temperature of the coil. I mean, that surface temperature is much lower. With the outdoor air temperature cannot reach the surface temperature of the coil. Right. Similarly here, the omega, I mean, there is no change in the water content. So omega remains constant, but the specific relative humidity is increasing. In that case, the relative humidity is increasing. I mean, if you are just cooling, I mean, if you are just cooling the room, although you are decreasing the temperature, but the relative humidity is also increasing. So that's why it is recommended that I mean, during the cooling process, there should be dehumidification process as well. That dehumidification process can also, can only be obtained if the surface temperature of the coil is lower than the dew point temperature of the air. So as a result, the dew, I mean, the vaporization of water vapors will be condensed when it will come to the surface of the coil. In our um, domestic air conditioner, this is happening basically. We are not achieving only cooling. Along with the cooling, we are also getting the dehumidification process. That's only because of so that the relative humidity is not increasing. Right? So in that case, the relative, if you're just a simple cooling, uh, omega remains constant, but phi value is increasing, right? If we look at the mass and energy balance, for example, whether it is a heating process or cooling process, whatever is the mass of the dry air at condition 1, it remains the same. So mass of the dry air is not changing. Similarly, omega, both in case of the heating and cooling, is not changing. And what about in case of cooling, we are adding heat. So heat added, heat addition, that will be basically the difference of the enthalpy. That means H2 minus H1. Similarly, in case of cooling, in case of cooling is basically the heat removed, right? The heat absorbed by the chilled water or the heat absorbed by the refrigerant is again the difference of the enthalpy. Only the sign will be different, right? But we are taking the positive value, right? When we don't put mass, that means this is kilojoule per kg, right? If you know the total mass of the dry air, then the unit will be equal to kilojoule only, because you have multiplied with the mass of the dry air. Now the next one is bypass factor of the heating and cooling coil. Bypass factor mean in the coil, whether it is a heating coil or the cooling coil, it cannot heat or cool all of the air passing through it to the coil surface temperature. So that's why, let's say, let's see this figure. Let's say this is the outdoor air, right? When the outdoor air enter in that duct, then there is a cooling coil. So that means all of the air cannot, come in contact with that cooling coil. Some of the air will not be in contact. It will pass through. So that's why we call the bypass factor. So bypass factor is basically the representation of the fraction of that air which is not in contact with that coil. So that coil could be the heating coil, it can be the cooling coil. For example, the total mass of the air which is entering is, let's say, 1 kg, right? So out of 1 kg, some of the mass of the air will be bypass. So let's say that bypass air mean its temperature is same as the inlet temperature because it is bypass. Whereas the remaining air out of 1 kg mean 1 minus x, this air will be in contact with that coil, right? So as a result, this air has a temperature equal to the outlet air. Let's say that temperature as a result of the cooling or heating, its temperature will be changed. So that's called, let's say, TD2. So that's called the outdoor temperature. So you can see we can also to calculate that bypass factor, that how much fraction of the air is bypass, we have to apply the mass and energy balance, right? Let's say if you apply the energy balance, let's assume that first that coil is a heating coil. So for that heating coil, if you apply the energy balance, what is happening in energy balance? Let's say initially it was 1 kg. So 1 kg is now we have the 1 minus 1 kg with the coil. The remaining x kg is bypass, and outlet we have the same mass. So this 1 minus x multiplied by the TDT, this temperature. Similarly, x is at the temperature of TD1. Again, the air which is leaving is total, 1 kg at temperature equal to outlet air temperature. So that mean that x that X CPT, that energy enthalpy is basically MCPT, right? That enthalpy is basically the MCPT, right? So that means this is mass. Mass means X kg. X kg times the Cp of the moist air, because we are considering the total air. Total air means the moist air. So X Cp TD1 plus 1 minus x CPM TD3 is equal to 1 CPM TD3, right? So as you can see, so CPM will be cancelled out. So if you rearrange, then you will get x time, this is x, this is also x, so that will be common. So we'll have the TD3 minus the TD1, whereas one of the TD will go on the other side, so it will be the TD3 minus TD2. So that value of the x, which is basically the fraction of the air which is bypass, so that's called the bypass factor. So bypass factor is basically the ratio of the TD3 minus TD2 divided by TD3 minus TD1, right? Let's say I'm giving you one example. Let's say the inlet air which is entering to the duct is with this value, let's say 60 kg per minute at 5 degrees centigrade and 100% relative humidity, right? So when it come in contact with the coil, all of the air cannot be in contact. Some of the air will be bypass, right? So bypass air, that means that will be at the same condition. So then the air which is in contact, that will leave that duct at 24 degrees C. Now we can draw this process on the psychrometric chart. I mean, this is this surface. I mean, this is the heating coil, right? Because we are using the steam heating, right? So if steam heating means the temperature of the coil is much higher. Let's say that's the temperature of the coil, and the inlet air mean 100% saturation. So this is on this line 100%, and the temperature is 5 degrees C. So 5 degrees C. So let's say we located the inlet point, and since this is a purely a heating process, so that means that will be a horizontal line. So we know the T2 temperature is 24 degrees C. So we can locate that 24 degrees C. So that means this is the complete process. And 3 is basically the surface temperature of the coil. We don't know that temperature, right? It's not mentioned. So let's say that's TD3, right? The surface temperature of the coil. So what is the value of the bypass factor? Bypass factor mean basically this is the process that take place. This is the inlet air, this is the outlet air, right? And this is the surface temperature of the coil. So basically this value is basically this value divided by the total value, that give you the bypass factor, right? Basically the bypass factor is basically this ratio. I mean TD3 minus TD2 divided by TD3 minus TD1. So that's basically the bypass factor. So this value, I mean difference of between T3 and T2 divided by the difference between T3 and T1. Right? Similarly, we can apply for the cooling coil. So instead, let's say this coil is now a cooling coil, then the refrigerant will pass through it. Right? So same formula can be obtained as we obtained in the case of heating. The only difference will be, I mean, the sign will be changed. I mean, instead of TD3, it will be TD2 minus TD3. Similarly, it will be TD1 minus TD3 in case of the cooling coil. Let me show you on the TS diagram. Let's say this is the cooling coil surface temperature, because cooling coil surface temperature is much lower. This is the outside air, right? So let's say the outside air, when in come contact with that cooling coil, its temperature will be decreased and let's say dehumidified. Let's say it reaches at 0.2, right? So that means what is the bypass factor? So this is the process that take place between 1 is the inlet condition and 2 is the outlet condition. So this is the bypass. I mean, this is the bypass between 2 and 4. So basically this is the ratio of this one to the ratio of the total. I mean T1 minus T4, sorry, T2 minus T4 divided by T1 divided by T4. I mean, this way you can calculate the bypass factor. And this temperature has a special name. It is called apparatus dew point, right? That the apparatus dew point is the surface temperature of the coil. That's also called the apparatus dew point. Dew point we say because when the outside air come in contact with the cooling coil, then the vapors present in the air that condensate. That's why the surface temperature of the coil called apparatus dew point. At the temperature at which the vapor present in the moisture, they condensate, they transform into condensate. That's called the apparatus dew point. So in that case, that 4 is basically the apparatus dew point. I hope you understand that. We can also represent a bypass factor in terms of instead of dew point temperature, or we can also represent in terms of omega value. I mean, instead of TD2, we can also represent omega 2 minus omega 4, because that ratio will be the same. Similarly, even sometimes you can represent in terms of enthalpy as well. You will get the same fraction. And then we have defined efficiency of the heating and cooling coil. I mean, how efficient is that heating coil or cooling coil? The efficiency, that term we called 1 minus BPF. I mean, if you subtract, I mean, 1 mean the 100% efficiency, right? Bypass factor will be, let's say 50%, 70%. So 1 minus the bypass factor is known as the efficiency of the coil, or the contact factor. It is also sometimes called the contact factor, right? This is the bypass factor. And what is the contact factor? 1 minus BPF, right? It is also called the efficiency of the coil. So in above case, we have the efficiency of the heating coil, which is equal to 1 minus the bypass factor of the heating coil. And the bypass factor of the heating coil, as we have calculated, this one is that 1 minus this value. So if you take the LCM and you simplify, you will get this efficiency. Similarly, we can calculate the efficiency of the cooling coil, which is equal to 1 minus the bypass factor of the cooling coil, this one, right? Again, if you take the LCM and simplify, you will get the efficiency of the cooling coil. So do you have any question up till now? So is it clear to everyone? No question? Right. So I think this is enough for today's class. We'll continue from here. I think we have some time. This is 5:04. Let's continue. I think we have time. We can have 10 minutes more, right? So this is for the efficiency of the heating and cooling coil. And the next one is humidification or dehumidification process. Now, humidification or dehumidification process mean when the state of the air is altered along the constant temperature. I mean, the moisture in the form of vapor, they are transferred into the system or they are removed from the system. When this moisture are added, we call the humidification. When the moisture is removed, they call the dehumidification process. As I explained earlier, if we are increasing the omega value will be increased from bottom to top. That's called the humidification process. Similarly, when the vapors are removed, they are from top to bottom, right? Basically, the moisture added or moisture removed, that's basically the difference of the specific humidity. I mean that G mean the mass of the water vapors that are added or removed. That is basically equal to, in that case, let's say omega C minus omega B multiplied by the mass of the dry air. So this is basically the mass of the water vapor. That will always be equal to the difference of the humidity ratio. I mean, let's say in that case, let's say omega C minus omega B, right? Since it has the unit of the specific relative humidity is the kg of water vapors, right? Kg of the water vapors per kg of the dry air. So if you know the mass of the dry air, I mean, if you multiply with the mass of the dry air, let's say mass of the dry air, right? So that means instead of per kg, you have multiplied the mass of the dry air. So that will give you the mass of the water vapors only, right? So I hope you understand, right? So if you have any question, you can ask me. So I hope that is clear to everyone.